Well, first of all, thank you very much for the kind invitation. It's my first time in Japan, and I'm really enjoying it very much. I really like it in here, so thank you very much for the invitation. So yeah, I'm going to speak about the MongeAmpére equation, and I want to start from the more classical theory for the local MongeAmpére with some motivation, some applications, and speak a little bit on the ellipticity properties, regularity, and the generality of the equation. And then I want to move from there to more recent results, where we introduced the non-local MongeAmpére equation. I will motivate it and give the main results. The results I'm going to talk about in the second part are in this paper with Luis Caffarelli on a fractional MongeAmpére operator. I put a picture to make it nice, so otherwise it's very boring. And now let's start from the beginning with the classical local MongeAmpére. And the beginning actually goes way back to the works of Monge and Ampere you see in the 18th century and 19th century. 1784 was the first work of Monge where he introduced the MongeAmpére equation into dimension. This was about the time about the French Revolution, more or less. Okay, so what is the MongeAmpére equation? The MongeAmpére equation is the determinant of the Hessian of a function u. And what we are doing is to prescribe this determinant, making it equal to function f. And basically, it prescribes the product of eigenvalues of the Hessian. It is a fully nonlinear equation. Okay, it's a nonlinear in the Hessian of the function. And it is elliptic. This is a funny feature. It is elliptic only when u is strictly convex and f is positive. I will come back to this later. The positivity of the right-hand side, you can see it here. If you have that your u is strictly convex, then the determinant is positive. So f positive is a compatibility condition. If you don't have that, there's no way. Okay. And just to compare with the model elliptic PDE, the Laplacian. The Laplacian is the trace of the Hessian, and in this case is the sum of the eigenvalues instead of the product. And in this case, well, this one we know it very well, is linear. And actually, I will say more about this in a moment, is the linearization of MongeAmpére in appropriate coordinates. So this will also play a role here. Okay, about applications of MongeAmpére, there are several that I have seen. The prescribed Gaussian curvature problem or Minkowski problem. You have applications to optimal transport, construction of antennas and reflectors, and also to meteorology through the semi-geostrophic equation. Okay, but the ones I'm going to talk about are the first two, the prescribed Gaussian curvature, the Minkowski problem, and some on optimal transport. Let me describe the problem, the setup a little bit. In the prescribed Gaussian curvature, we are going to do it for graphs. Okay, so we are going to be looking at the hypersurface of class C2 that is given by a graph xn plus 1 equal to u of x around some point x0. Okay. So then we can compute the principal curvatures of S at x0 that are by definition the eigenvalues of the differential of the Gauss map. The Gauss map is the normal to the surface at each point. Okay? And if we compute this for the graph, what we find is that the principal curvatures are the eigenvalues of this matrix here. This differential of the gradient of u over the square root of 1 plus the square of the modulus of the gradient of u. Okay? So now, the Gaussian curvature of the surface at a given point x is just the product of the principal curvature. So we can write it down, since we know that the principal curvatures are eigenvalues of that matrix, we can write it down as a determinant, right, of this complicated matrix. And if we do the computation, we find out we can write it down in this way. We can write it down as the determinant of the Hessian over the 1 plus the square of the modulus of the gradient of u to a power n plus 2 over 2. Okay, so you see already there the Monge-Ampére operator. And if you want now, you can go the other way around. Instead, here I was saying I know the surface. Now you could say, okay, if I give you a given curvature at each point, can you find for me a surface that is a graph that fulfills this restriction? That is the Minkowski problem. Find a surface that has this given curvature k of x. And actually, this is a problem like the one we were talking about, only a bit more complicated because the right-hand side doesn't depend only on x, but also on the gradient of u. But you see that actually the gradient of u appears here in a very natural way. Okay. Just a comment on it. The Gaussian curvature has a very nice topological and geometrical properties. One of them that for me is very striking is the Gauss-Bonnet theorem that basically relates the topology of the of the surface to the total Gaussian curvature. It says that the integral over the whole surface of the Gaussian of the Gaussian curvature is a constant 2 pi times the Euler characteristic of the surface. That is 2 minus 2g. G is the genus, the number of holes. Okay, I find this beautiful, so I couldn't resist to mention it. And another result where you can see the Gaussian curvature is the Gauss's theorem egregium. Sorry about that. Theorem egregium in Latin means remarkable theorem, and it was Gauss himself saying, okay, this theorem is remarkable. What he found out is that the Gaussian curvature of a surface is invariant under local isometries. If you want to see it in a visual way, we can see it with a slice of pizza. A slice of pizza has 0 Gaussian curvature. Okay, so it doesn't really matter how you bend it in a space. One of the directions must remain flat. So next time you eat pizza, you can think about this. It's easier this way. Okay, so the Italian way, let's say. So another application that we can see easily for the Monge-Ampére operator is the problem of optimal transport. Okay, optimal transport, we can formulate it as moving a pile of trash or sand or rubble to some hole, an excavation, with the least cost. So it is transport, but it is optimal in the sense that you minimize the cost. And in French, this is called Deblay-Remblay. So in case, this is in the title of the original paper of Monge, that it talks about the theory of the Deblay and Remblay, the piles and excavations. So this is basically the idea. To formulate it in modern terms, mathematically, instead of thinking about a pile and a hole, we can think about 2 piles to have 2 densities, 2 mass densities that are positive. And what we are going to do is to reshape one of the piles into another. Okay? The only thing is that we don't want to lose mass along the way. So we want this condition of mass conservation. The total mass in the beginning is equal to the total mass in the end. And then the problem is to find a map that minimizes the total transportation cost. The cost is just a sum, an integral of the masses at each of the points times a function of the distance that these masses are traveling. So if we are going from x to t of x, here we have some relation with that distance. Here I'm writing with a square. You could consider other costs, but this is one of the classic ones. Now, of course, you want a compatibility condition. That is that you want your map T to send the first pile into the second, to push the mass F onto G. Okay, and you can write down that condition in this way. The integral of G equal to the integral of F over T minus 1 of A for every Borel set A. Okay. Before going on to find MongeAmpere in this problem, let me just mention 4 key moments in this problem. Keep in mind that it's a problem that has been around for more than 200 years. So the first milestone is when Monge, in the beginning, heuristically shown that if, and I stress if, a cost minimizing map existed, then it had this form. It was the gradient of a convex function. Okay? I'm saying if because he didn't actually show existence. Okay? And this happens to be a very hard problem. It actually took like 150 years. I'm sorry, I don't know what happened with my voice. It took like 150 years until Kantorovich was able to show existence, but not of a solution to the problem, but a solution to to a weak version of the problem. I think I'm losing my voice in the worst possible moment. Okay. Now, he's shown existence to a weak version of the problem, so it remained open if this solution was actually a solution of the original problem. Okay, so then Brenier in the 80s gave a rigorous proof of existence and uniqueness of an optimal map, a solution to the original problem, characterized by convex potential. Convex potential as in here, the gradient of a convex function. And this was done for the quadratic cost that we were talking about. Then some other costs were considered, and there were basically 2 types of costs. The ones that were a power or similar to a power, and then the one that had power 1. The one where the cost is just the distance that you travel. And that one was the most difficult one, and it was finished in 2001 and 2002 by Trudinger-Ban and Caffarelli, Feldman, McCann. Okay, so what is the relationship with MongeAmpere? From the admissibility condition, what we can do is to change variables y equal t of x, and immediately from these integrals, what we are going to get is a prescribed Jacobian equation. Okay, we see that the determinant of the gradient of t is involved, and then if we remember the result from Brenier, that t is a gradient of a convex function, what we get is a second derivative. And we actually can take out the absolute values because since it's a convex function, it's positive. So what we get again is a MongeAmpere type equation. Again, it naturally depends on the gradient of u. Okay, and here the restriction u convex that I was talking about in the beginning comes out completely natural. Okay. So let me, now we know about the equation, where it appears, let me mention why it is somehow difficult. A classical way to show that, that a solution to equation is regular is to take derivatives of the equation, especially since here the equation is a determinant, that is a function that is products and sums. No? So we can differentiate in a given direction E, and then the derivatives of the solution are going to satisfy a linearized equation around the solution E. I have computed it for you here. In this case, what we get is a linear equation in trace form, and we have a matrix of coefficients here. that is given by the matrix of cofactors of the Hessian of U. Okay, the matrix of cofactors, just to refresh, is the matrix that we find when we compute the inverse of a matrix. Of course, if the Hessian is non-singular, but if it's singular, you still can compute the matrix of cofactors. So, okay, we have a linear problem with coefficients in trace form. The question is, how bad are these coefficients? Okay, if they are not so bad, we have already regularity estimates that we can apply, so we are done. Well, looking at the matrix of cofactors, the eigenvalues of that matrix are a product of n-1 eigenvalues of the original matrix. Okay, so with that, we see that searching for strictly convex solutions, it's absolutely natural. Because if not, you cannot guarantee that the equation is elliptic. Okay, so forget about elliptic estimates. Even so, if you have that the solution is strictly convex, the cofactor matrix is going to be positive definite, but you don't have control on the eigenvalues. So it is elliptic, but degenerate elliptic. In principle, depending on the point, it could go to 0. If we want something uniformly elliptic, as in the theory of Caffarelli, Cabré, or the fully nonlinear theory, what we need to show, and this is a key point in the theory, is this bound on the Hessian of U. We need to show that the Hessian of U is bounded from above and below, but by a constant times the identity. When this happens, the equation becomes uniformly elliptic, and regularity estimates are available. This is absolutely key in this theory, because in this theory, actually, the solutions, the right-hand side, and the coefficients are all the time about the same. Okay, so what happens to the solution transfers to the coefficients and to the right-hand side. So it's all tied together somehow. This idea is going to be crucial also in the non-local case. And speaking about non-local case, let's move on to the second part. That is the non-local Monge-Ampére. Well, you probably know, but non-local equations arise in all kinds of optimal control problems that involve jump processes. Okay, this happens, for example, in financial mathematics. And they are called non-local because in order to compute, to check if a non-local equation holds at a point, you need to use the information not only around the point, but also far away. So they are non-local in that sense. And this, another fact that is interesting is that local PDE are usually limits of non-local PDEs. Let me recall here, I'm going to need to use some definitions. Let me recall all of them in a table. So in the local case, we have the Laplacian. That is the trace of the Hessian. The corresponding non-local operator, the fractional Laplacian, is given by this integral. It's the integral of uy minus ux over y minus x to the power n plus 2, the principal value. Okay, there are other definitions. They are all equivalent. This is the one I'm going to use. Then we have seen linear operators, local linear operators in trace form. Okay, trace of a matrix times Hessian of U. Here I'm writing the coefficients in a funny way. You will see why later. But it's more convenient to write them in ATA form. It's just I'm writing the T on the last one, so it would be more like at. But anyway, the important thing here is that these are the Laplacian of a linear transformation of U of A of x. So you can just go on to the non-local world and say, okay, the fractional equivalent, the fractional, let's say, trace operator, are the fractional Laplacians of a deformation of U of A of X. A is a matrix. And the only difference with the previous definition is that now here we see A minus 1 in the kernel, in the denominator. Okay? I write them in this form, A transpose, because this way you have here just A minus 1. Otherwise, you will have the square root. It's more comfortable for us this way. And then, of course, you have the determinant of the Hessian of U, that in the non-local case is a big question mark. So what would be a non-local equivalent of the determinant of the Hessian? That was the question. And in principle, there is no canonical definition of determinant, because the determinant is a notion that is very associated to the matrix, to matrices. So this is what we did in the paper with the Schiaparelli, and then there are some other operators around that are related. There is the work by Guillen and Schwab that use a restricted version of a non-local operator. You have the work by Caffarelli and Silvestre that instead of, well, I'll tell you the difference later. Then you have Maldonado and Stinga that is very recent that actually do a fractional linearized Monge-Ampére. And then this was like a month ago, a preprint by Wu that does a type of Cartesian equation that extends this result. This is what is around. So let me motivate the definition of the non-local Monge-Ampére. It actually comes from this linear algebra identity that I find, if you have interest in the AVP estimate, this is very related to the proof of the AVP. Basically, it says that the 1/n power of a determinant of a positive matrix, positive symmetric matrix, can be written as an infimum of linear operators in trace form. Okay, it's an infimum of trace of A transpose BA with the matrix A having determinant equal to 1. To me, this was very striking the first time I saw it, but after some thinking, it's basically the arithmetic geometric mean inequality. To prove it, you just, well, since the matrix is symmetric, you can just write the trace as a sum. Then the sum of n numbers over n is the arithmetic inequality, is bigger or equal than the geometric inequality. That is the product to the power 1/n. And that is the determinant of the original matrix. But since we are assuming that the determinant of A is equal to 1, you can factor it out. And you're good. So this is one inequality. But then you are able to guess what is the optimizer. So this particular choice of the matrix A has determinant equal to 1 and actually makes an equality. So you have that formula with the minimum action. With this characterization, we can write Monge-Ampére as an infimum, as a Bellman operator. If you notice here, is an infimum of linear operators in trace form. And if we go back to the initial table, this gives an answer to the question mark, because we can replace the local linear operator in trace form by the non-local counterpart. Okay, and then we get this D of SU, D is for determinant. That would be the definition of our non-local Monge-Ampére. Okay, so it's a Bellman operator, basically, with the condition that the coefficients have to have determinant equal to 1. Some nice properties. Sorry. One nice property of this operator is that when the order of the equation converges from local to non-local, from non-local to local, sorry, actually converges to the determinant of the Hessian to the 1/n. For that, you need to scale properly the operator. This is usual in the non-local literature. And then one not so nice feature of the operator, or, well, it is nice in the sense that you can write a paper over it, but is not so comfortable is that it's degenerate. The degeneracy of this operator, you can see it very easily in 2 dimensions. In 2 dimensions, the determinant of the coefficients equal to 1 means that the 2 eigenvalues are reciprocal. So one can be as small as you want at the expense of the other one that will be as large as you need. Okay, so you don't have a nice class of matrices that are in between 2 constants. So no uniform ellipticity in principle. Okay. But let's put it this way. So the main results in the paper are an application to this problem, where you have this new operator equal to u minus phi. Phi is C2 alpha asymptotically linear function that is strictly convex in compact sets. Okay, this problem came from geometry, and the nice thing it has is that the phi itself is a sort of boundary data at infinity. It's a problem defined in the whole space, and it doesn't have the Dirichlet boundary conditions that in the non-local case are an extra pain. So we were separating the difficulties here. What we proved was a comparison principle for viscosity solution, existence and uniqueness of solution, Lipschitz continuity of the solution, and semi-concavity. Semi-concavity morally means that the Hessian of U is bounded above. If you cannot write the Hessian, you can still write the second order difference, okay, that would be bounded above. And when you are in this situation, you are basically back to the situation I said was good in the local case, where you actually have control on the Hessian. Okay, so now in my opinion, the nicest result of the paper that applies to other problems than this one is that you can show uniform ellipticity of the non-local MongeAmpére with this property, once you show that the U is semi-concave. Yeah, basically that was what I was going to say here. In the non-local case, linearization is not possible as in the local case. Okay, so we need to find a way to go around. You remember I linearized the MongeAmpére operator, and I said, okay, if I have that condition, the coefficients are uniformly elliptic. Since now we cannot do that, we have to find a way around. But the good news is that it is possible to do that. How much time do I have left? Perfect. Okay, I was a bit worried. Perfect. So this is the main result of the paper. This is the result. This result actually we wrote it in a way that could be applied to other problems. Okay. Here, what you are saying is that if you have arrived to a point where you know that U is not to degenerate, you can show that the operator is actually uniformly elliptic, as in the local case, and then you will be able to apply the results, the regularity results for a uniformly elliptic equation. Okay, that's the moral of the story. Basically, the conditions you have here is that U is Lipschitz and semi-concave. Okay, S is the parameter of the equation, is in between 1/2 and 1. This is for 2 reasons, because we want results that are stable in the limit from non-local to local. The local case would be S equal to 1. And also because if you are below 1/2, basically you don't gain regularity using, for example, Levans-Krylov. So it's kind of pointless to do the whole thing. So this is the case where it matters. And then you need bounds from below on the non-local MongeAmpére operator. And here I'm normalizing it with the factor 1 minus S as before. That is the one you need to pass to the limit, because this result is stable in the limit as S goes to 1. Okay, all the constants involved here converge nicely to the ones that appear in the local case. And actually, line by line, the proof converges from non-local to local, which is quite amazing in my opinion. This is the key line when I'm saying that the operator becomes uniformly elliptic. What I'm saying is that actually you can find the constant theta positive such that the non-local Monge-Ampére that we have defined that has coefficients that have just determinant equal to 1 but no control on the size, that infimum can be computed in the restricted class where all the matrices have the smallest eigenvalue bounded from below. I could have said also from above, because since the determinant is equal to 1, if you block the smallest eigenvalue, you are automatically blocking the largest one. Again, in 2 dimensions, this is very easy to see because they are reciprocal. So if the smallest cannot be very small, the largest cannot be very large. Okay, this is something we need to keep in mind all the time. Okay. So in the proof of this uniform ellipticity theorem, there is a key estimate, that is this one. That what this estimate is telling you is that when you look at the linear operator in trace form, a non-local one, you can find a bound from below that depends on the smallest eigenvalue of the coefficients to a negative power. The most crucial thing here is that the power is negative. Why? Because then if the smallest eigenvalue is very small, the operator is large. Okay? And that's crucial because here is how we prove the theorem using this estimate. If you consider the infimum of the linear operators in trace form over the class of matrices that they generate, let's say that the smallest eigenvalue is smaller than a given constant theta, then that infimum is going to be bigger than a constant times theta to a negative power because of this. All the operators in the class are bounded from below, so the infimum is bounded too. Okay. So this means that infimum in the class of Bath matrices is large depending on theta. At the same time, there is one operator in this class that is the fractional Laplacian that is fixed. Okay, so we know that the infimum in the whole class of matrices unrestricted is less or equal than that operator, than the fractional Laplacian. And the fractional Laplacian is bounded because your function u is semiconcave. Semiconcave, yes. So it's bounded from above by a constant m times c. So the situation you have here is that the infimum over the unrestricted class is bound to be small, and the infimum over the class of Bath matrices can be large. So what you can do is to choose theta in a way that is strictly bigger than this constant n times c. And in this way, the infimum over the class of Bath matrices is strictly larger than the infimum that we are looking at. Okay, so let's recap. So we take the infimum over the class of unrestricted matrices is strictly small than the infimum if we look only at the Bath matrices. That means that we can just look at the good one. Okay, we can fix some theta that is given by this condition, right? We can fix some theta such that the operator ds is equal to the infimum over the class of matrices that are not too degenerate. So in some sense, what you are saying here is that these matrices are somehow a bit round. Okay, it may be like an ellipsoid, but not a very degenerate ellipsoid that looks like a line. Okay. Keep in mind that when you stretch an ellipsoid to keep the determinant equal to 1, if one axis is really large, then it's very thin in all other directions. Okay. So yeah, we need to focus our efforts in improving the key estimate, the lower estimate on these linear operators. And this proof has 2 ingredients. The first ingredient, and this resembles a little bit what you do in the local case. The first ingredient is that you need an uniform bound of the one-dimensional fractional Laplacians in all directions. Okay. Before looking into this, what you would be saying here in the local case is a uniform convexity estimate. What you are saying here in the local case is that the second derivative in every direction is bounded from above and below, and it's positive. Okay. In this case, what you are doing here is this is like, in a way, a fractional second derivative. Okay, is a fractional Laplacian in the direction E, right? We have it here. It's the integral over R, and here we have, instead of n, we have 1, and we have that is bounded from above and below by two constants. And the important thing is that the constants are uniform in the directions and positive. Okay, this result actually is quite amazing, but if you think about it, it is natural that this happens when you have the semiconcavity condition. Okay, somehow the semiconcavity is what is blocking the degeneracy of the equation. And then you will see that we will need this kernel estimate. Is an estimate on the size from below of the integral over the sphere of our kernel, the kernel we are dealing with. And if you notice, here appears the second important thing. It's the bound from below depends on the eigenvalues of the matrix that appears on the kernel raised to a negative power. This is where the negative power in the estimate comes from. Okay, so how to prove, using these two ingredients, how to prove the key estimate? Well, the first thing, you just have to write the quadratic form, a minus 1y in modulus. You can write it down as epsilon j squared yj. Okay, and just this epsilon j squared are going to be the eigenvalues of a minus 1. It's an easier way to write it. And then you write it, that integral in Rn, in polar coordinates, only that you put the directions outside. Okay, and what you have inside is actually a one-dimensional fractional Laplacian in the direction E that we know are bounded. So somehow what we can do is we can factor this out of the integral because it's bounded below by a constant. Okay, and then what we are left with is the integral of the kernel over the sphere, the one I was saying that we have the kernel estimate. And with this kernel estimate, what we get is the sum of the epsilon j's to the minus 2s, and working a bit with the eigenvalues, we can just take the smallest of the epsilon, that is actually the largest of the lambdas, because these epsilons were the eigenvalues of the a minus 1. And then in the last step is just cosmetics. You can leave it with the largest eigenvalue you want, or you can pass to the smallest using the condition that the determinant is equal to 1. Okay, you can use either one. And there you go. You have here the negative power of the lambda mean. How much time I have left? Oh, okay, fantastic. It's just, then I go in detail on the proof, otherwise I will just skip. So with this, we are left with two questions. We need to show the uniform bound, okay? Now we have left, and we have to show the kernel estimate. To prove the uniform bound, it is easier if we do it in 2 dimensions and we consider, instead of a general direction, just parallel to the x-axis, direction 1, 0, for example. So basically, what we know from the setup of the theorem is that our non-local Monge-Ampére operator is bounded from below. Okay, that's the information we have. And since it's an infimum, the way you do these proofs, the way you can work with this operator is that you can bound it from above with any choice of linear operators that you want. Okay, so in particular, what we can pick is a matrix that is diagonal and has eigenvalues epsilon and 1 over epsilon, so that the product is equal to 1. And then we have the freedom to pick this epsilon in the end. Okay? So you write down what you have, and the trick is to add and subtract this quantity. Is the kernel is the same, just the operator, the numerator is u of y10, okay? And then you rearrange terms like this. Here I have already done some computations, right? If you subtract the u y10, then you have u y1 y2 minus u y1 0. What you can do is to apply the semiconcavity and its discontinuity that are the other hypothesis of the theorem that we haven't used yet. It's here where you use them. And what you get is this condition. What you get is that this difference, the difference that is not written here, this minus this, is less or equal than the minimum of the Lipschitz constant times the modulus of y2 and the semiconcavity constant times the modulus of y2 squared. Important thing here, this depends only on y2. And then the remainder, that is this y00 and the plus u y10, just happen to depend only on the first variable, on y1. So what we can do here is to factor out the variable that corresponds to what we have in the numerator. We factor that out from the kernel, and we do a change of variables for what we have here. C equal epsilon squared y1 over modulus of y2, and the corresponding one here. There are these epsilons there that come from the computation. And what we get is a constant, this first part, that is like epsilon to the power 2s. And for the second part, what we get is a power epsilon to the minus 2s times actually the integral that we had in the beginning, the one we were aiming for. This is the fractional Laplacian in one dimension in the direction of E. And see, if you remember, I said that I would choose epsilon near the end. Now it's the time. Now we can choose epsilon that is small enough so that this term here can be absorbed by the right-hand side. Okay. Notice that we have 1 minus s here, very important, 1 minus s there. This is what is going to make this pass to the limit. And okay, this negative power maybe will grow a little bit with this choice, but it's still a constant, so no problem. We make a choice here in a way that this is half of eta 0, and that's it. We plug here whatever we need, and we find mu 0s. Then we have to prove this one, the mu 1s, but that one is easy. That one comes from semiconcavity. It's almost automatic. Okay, and this will be the proof of the uniform bound. And then to prove the kernel estimate, this one took some time until we learned that this was what we needed. No, but once you know it, the proof is fast. First, you need to show that first identity that it's maybe the trickiest, but it's just a computation. That you can write the integral as you see. You can rewrite in a way that what was in the kernel in the denominator goes to the numerator, and you are changing the epsilons to epsilon to the minus 2. Okay, but once you have that, then you are just applying Jensen inequality. Okay, and then you integrate by parts, noticing that you can write here modulus of y and go for it. And you get the key point here, this sum of epsilon y to the minus 2s. This negative power is the key point. And the reason why you don't really need to bother doing this careful kernel estimate if you only want the result. You need to do this if you want the result to pass to the limit. So this was the reason why we needed to do this more carefully. But this is crucial when you want the result to pass to the limit. And this finishes the the proof of the theorem, because this is the missing ingredient in the crucial key estimate, and that was what allowed to prove the theorem. And that's it. That's all I wanted to say. So thank you very much for your attention.